Okay, so we start talk. This is on page 12 of your book. Okay. So let's work out what talk is. It says to define talk, and talk is simply the turning effect a force has on an object. When we push an object, either in the world that I've been teaching you in physics for the last year and a half, everything seems to slide and slide well. But objects don't slide if you push them. You've been pushed in the back, you don't always just slide forward, you tumble, fall over, fall back, and so on. So objects that are pushed through what we call the centre of mass. Now, I've got it here as the centre of gravity. Accidentally, it's an old-fashioned term. We don't call the centre of gravity anymore. It's called the centre of mass. Okay? So an object's centre of mass is where you could push an object in such a way that it will slide and not turn. Just to take a martial arts idea, and we've all seen The Matrix, hopefully. If not, get it out. Good movie. So Keanu is really, what his name is? Keanu. What was his name?
Keanu Reeves.
Yeah, okay, rightio. Now, if I was to take a person, and there's the person standing sideways, arms there, and I was to push them high on their chest, they would fall back like that. If I was to undercut them with a nice roundhouse, you all know that roundhouse kick, okay? The legs would go out from under them and they would fall forward like that. If I get the exact right position, which is just a little bit lower than your sternum, and push directly there, I will make you go fully backward. The whole of your body will go back in one go. You might start to do a bit of a curve like that, but you'll start to slide back. That's because your centre of mass, your centre of gravity in the old days, is placed just underneath your heart. So if you're pushed there, you should slide back, or be translated, as they say in maths, backward. So when you press or push through the centre of gravity, the centre of mass, the object should slide, as long as friction is able to be overcome, of course. If you were to push above or below the centre of mass, then the object will somehow tip. And this tip will give a turn to the object. So if I was to push up here, if I was to push in this diagram up here, oops, wrong thing, a little bit, up here, then obviously just by common sense, what will happen to the green rectangle? Right, it will start to turn. It will turn or twist in this direction. Okay? That part will fall this direction and this part will go up that direction. Okay? If I was to push in the other direction, if I was to push down here, then what will happen to the feet of this object? It would rotate that way and the head would rotate that way. So there would be imparted a turn. This turning effect is called a torque. So torque is a turning effect a force causes when a force is applied to an object that is not through its centre of mass. Okay. Have a look at that. So, what is the formula for torque? How do we measure it? If we're talking about torque, sorry, that's always an old joke. All physicists say it. Yeah. So, how do we calculate torque? Well, firstly, we're going to give it a letter, and the letter is this tau. Okay, it's the letter T from Greek. Okay. If you want to just use a T in your exams, that's fine with you. Okay, with me as well. Okay. So there is torque. That's the And obviously the F and the D stand for force and distance. That's it. It's one of those, as I've always said about physics formulas, is that the majority of them are just so straightforward. Okay? Torque is force multiplied by distance. Okay? So it's calculated by the product of the applied force and the distance from the centre of turn. Now, we know the name of the centre of turn down here is called a pivot point. Okay? Now, in most times, pivot points are not fixed. So at the moment, if I was to be pushed in the back of the head, I would just fall forward. My pivot point would be my feet. Okay? But my feet are not fixed to the ground, so I would also slide and so on. If we were talking about a handle on a door, then this would be where the handle is attached to the door. Okay, the point of turn, the fixed point. And the distance is from the point of turn to the end multiplied by the force that we apply. Okay? So the distance is measured, The distance is measured from the point of application of the force to the centre of the turn, also known as the pivot. I don't know why it's still measured. Okay. Are we okay to move? What? Just pausing. Looking at this diagram, here's the one that appears in your book. We can now compare what torque does and how much turn it imparts. Before we do, what do we measure torque in? The unit of torque is called the Newton Metre. It's a silly looking or sounding unit. Remember, torque is equal to force times distance. If force is measured in newtons, then and distance is metres, then it must be torque is measured in Newton metres. Okay? We haven't given it we haven't named it after somebody, so it's still the Newton metre. Hopefully one day they might.
The Rebecca.
No, I'm not going to call them Rebecca. I know she can talk really well, but okay, anyway. Oops, right. Let's have a look at these four diagrams. Just by common sense, let's see which of them would cause the object to twist the most. So remember, in all of these diagrams, they are fixed at this end. So there is a fixed pivot point here. Okay? In the first diagram, I'm going to apply, they all have the same force applied. Okay? This one here I'm applying at right angles. This one here is starting to apply the force, but it's starting to apply it at an angle. Remember, a force is a push or a pull. So here we are pulling it here at right angles, straight up. Here I'm pulling at an angle. This one here I'm pulling at a very, very steep angle. Okay? And this one here I'm pulling directly out like that. Which of these four situations would give you the greatest twist? It's the first one, isn't it? Okay, so this one here, we can say the torque is maximum. Okay? And we're going to come up with a reason for this maximisation. Looking at the last one over here, will this cause any twisting or turning? No. It's like taking a door, okay, and rather than pulling at right angles to the door, I try and open a door by pulling this direction with the handles, okay? There is no turn, is there? So torque is zero. So looking at our door again, because the door is a great example of a twist or a turn, I'm opening, the first here is where I pull directly straight out at right angles towards me, okay? The second, the last one there, the fourth, is where I pull directly against the hinge. Number two is where I open, and I'm opening the door at this angle here. So I'm pulling the door open in this angle. Notice my arm and the door make an angle. How much do I give this one? It's not that easy to pull it, is it? Okay. And what about when I'm really opening the door at this angle? It's not easy, is it? So what happens as the angle gets bigger and bigger? Torque starts to decrease. So this is reducing or reduced torque. This is very little torque. All the way down to zero torque. So as the angle between the force and the actual thing that we are twisting or turning gets bigger and bigger, the torque reduces down to zero. So we must be able to modify our formula so that it will reflect this. Okay, so we start with, is everyone agreeing that at 90 degrees we have maximum torque? At 0 degrees we have zero torque. So we need a function that is maximum at 90 and minimum at 0. It's the sine function. Good. Oops, my reveal. So the formula is going to be modified to tau, or torque, equals FD sine theta. So could you write that down? There's a position that says underneath this. That's where you've got to come up with the idea that we have to have torque equals FD sine theta. So theta is this angle between the bar that's turning, or the object that's turning, and the angle of the force. Being a sine, does it matter if it's the acute or the obtuse angle? No. So remember, sine is a very forgiving thing. So you can talk about this angle or that angle, it doesn't matter. Okay? It's still measured in Newton meters. Are we okay that the formula is FD sine theta? If it's at 9 degrees, we drop the sine theta. Okay, moving on. Just like we have two forces, if we have a push on one arm and a pull on the other arm, we can work out the net forces on an object. We can also do net torque. If we have two things twisting, and we often do have two things twisting. Imagine you've got to open a tap. Oh, actually, how about a wheel on your car? Okay, on your steering wheel. When you steer your steering wheel, you put a hand in one position. They call it the 10 and 2, don't they? And you use both hands, pull in opposite directions or turn in the same direction to help you turn the wheel of that car as quickly as possible. So here we've got two torques coming together. If they are turning in the same direction, by common sense, we add the torques together. If they are turning against each other, we subtract the torques. And we use clockwise or anti-clockwise as the descriptor. So looking at this one here, doing annotations, there is two torques. There is this torque here. Can you see that one there? Notice the angle is 90 degrees, so it simplifies everything. So what would that torque equal? Its torque is F times distance. The distance is 2 and the force is 5, so 5 times 2 is 10. And which direction would that make this bar, or whatever object it's called, rotate? Is it clockwise or anti-clockwise? It will go anti-clockwise. So this is anti-clockwise. Looking at the other torque on the other side, here is the other torque. There's the centre of turn right in the centre. It's a 3 metre distance and a 4 Newton force. So the torque here would be 4 times 3, which is 12. And it's 12 Newton metres. Is this a clockwise or an anti-clockwise torque? It's anti-clockwise. It's going in that way. That's anti-clockwise. So this one here, this is also anti-clockwise. If I've got a 12 anti-clockwise on this side and a 10 anti-clockwise on that side, would they add together to make a full turn anti-clockwise? Yes. So the total is 22 anti-clockwise. Or if you're in America, you'll say counterclockwise, which sounds silly. Okay. This is the diagram in your book, and we want to find the net torque on these children here on the actual seesaw. Okay. Is there two torques acting?
Yes.
Yes. Okay. So, are they acting in the same direction? Are they standing in the same clockwiseness or the rotational? The actual answer is no. The child in the yellow shirt, their torque would be going in this direction, which would be anti-clockwise, and the guy in the red shirt will be going this direction. So are the two torques countering each other, going against each other? Yes, one is clockwise and one is anti-clockwise. Does it make sense that it's like pulling against each other? Okay, so we're going to work out what is the winning torque. So we need to find out the force for this yellow fellow here. Okay? This fellow in the yellow shirt, he's 45 kilograms, and is 45 kilograms a force? No, that's a mass. So we can't say it's a force of 45. We've got to work out their force from their mass, and what we call the force that a mass creates. Weight. So the weight force for this fellow here would equal 45 times 9.8. Can I get a value? It's around about 450. 441. Okay. So this torque for this person here would be 441 multiplied by 1.2 metres. Okay. Giving us a torque of, for this on this side here.
529.2.
Sorry, 529.2 Newton metres, and in what direction would this be? That is in that way, which is anti-clockwise. Okay? So that's that side. Looking at this fellow over here in the red shirt, so we'll do this in red. Once again, we've got to calculate their weight force. So it's 60 times 9.8. And what value is that? It's somewhere about just a little shy of 600. 588. And that means that their torque would equal 588 times their distance. In this case is 0.8. And what is their torque? 470.4 Newton metres. And it's clockwise. So which of the two torques, the fellow in the yellow or the fellow in the red, would have a greater turn on this seesaw? The yellow. Okay, so he is the winner. By how much is he the winner? So overall, the net torque. Okay, now how would I write net torque? It's sigma tau equals this value minus that value, which is 58.8. We agree with that?
Yeah.
And what is the net winner? Which direction? Clockwise or anti-clockwise? Anti-clockwise. So it's Newton metres anti-clockwise. Okay, and you can write clockwise out correctly. Now, have we got any questions on that? Are we okay that the two torques are opposing each other this time rather than, like in the last example, they were going with each other? Okay, the final few examples are what would happen in this case? We have a weight which has a mass, I don't like to use the word weight, so this is a mass of 5 kilograms sitting here on the end of a bar. And it's got a pivot point over here, and it's a length. Okay? What would be the torque? Is this a 90-degree angle? Yes, so it's simply torque would equal force times distance, and in this case the distance L is given as 1.2. What is wrong with saying the force is 5? Right, that's kilograms, it's got to be converted to a weight mass, so I just simply need to, I could simply do, it's 5 lots of 9.8 times 1.2, and that will give me my answer in Newton metres. Greg, have you got a value for that? 58.8 Newton metres. Thank you very much. Do we agree? Okay. In this case here, and we often get examples of this. This here, if I've got A being 30 degrees, I'll just put that over here and make it slightly larger so you can see it. A is 30 degrees, is this angle here is 30. Now, is that the angle that the force is making? No, we need to find the angle here. That's the angle between the force and the object that is turning, isn't it? Okay? Or we could have, if I extended the bar up here, that angle there is the other angle we could be using, shouldn't it? Okay? The reason why we can use either of these two angles is because the sine function does not care about the acute or the obtuseness of my angle. But if this angle here is 30, can I use that angle up there here as 30? No. So that angle there by right angled triangle geometry is simply 60 degrees. So I'm not going to do much with this example here. It's just that you would use torque equals FD sine theta because it's no longer at 90 degrees. Force is 5 lots of 9.8. D is still 1.2. And this time is sine 60. Okay. Is it 50.92 Newton metres? Okay. Remember, if the force acts along the object or at 180 degrees to the object, like in this diagram here, where the force is acting towards the pivot point, then do I get any turning effect? No. Okay, because this angle is 90 degrees or, 0 degrees or 180 degrees. It's no longer any other angle. Okay? We won't go with that one, there's no. Oh, yes, we will. Final example. So I'm going to go larger. Right. This is from an old textbook. Here we have a 50 Newton force acting at 60 degrees, and the pivot point is 0.4 metres away. Is it any harder, even though it looks more complicated? No. Can I use this angle as 60? What happens, can I use that angle as 120? Yes, it doesn't matter. So torque would equal FD sine theta. This time F is 50, D is 0.4, and it's sine 60 degrees. And it's quite straightforward. Don't forget to, the actual answer is 32 Newton metres. Now, don't forget, because torque is a vector, because it's a product of a vector times a distance, it's a product of two vectors. It is itself a vector, so we have to supply, for completeness, the direction of turn. What would you say for this one? Anti or clock? It's anti-clockwise. So please don't forget to write at the end of Newton Metre that says what is the torque. Say it's clockwise or anti-clockwise, not just the magnitude of the torque. How's that? Okay.